Okay, so today we'll continue on with the SN2 reaction. So this is an ionic reaction where a lone pair of electrons or two electrons are moving, where the nucleophile is supplying those electrons to react with an electrophile that has a leaving group. And we're going to look at the factors that influence the SN2 reaction. So we'll look at the leaving group, the solvent, why a particular class of solvent is used, and then the stereochemistry of the SN2 reaction that's based on how the trajectory of the nucleophile approaches the electrophile due to the antibonding orbital. So as we move forward, everything that we learned in the first three modules is like coalescing together, and now we're applying it to describe these different reaction mechanisms. So what makes a good electrophile? And it's the nature of the leaving group. So the leaving group is the thing that is being substituted by the nucleophile. And the way that we rationalize sort of strength of a leaving group or what makes it good is going back to this pKa argument. So I'm going to write the nucleophile of this form where it's a formal negative charge, so we have that lone pair of electrons. And then we have some methane derivative with a leaving group. And so that nucleophile is attacking 180 degrees opposite the leaving group. We cleave that sigma bond, and the electrons then move on to the leaving group. So that leaving group has to be able to support the acceptance of those electrons and then bearing the negative charge. So the way that we make this connection with pKa and acidity, so for this thing, leaving group, if we look at these different halomethane derivatives, so the methyl group's staying the same, and we're just examining the features of the halogen. If you look at the CX bond, you can see that it increases moving down the group. And if you kind of visualize that structurally, the longer that bond is, the more it sort of resembles a product in the sense that it's easier to cleave a longer bond than it is a shorter one. And so when that X group leaves, it forms the halide anion. If we think of those as the conjugate base of its respective acid, and then we look up the pKa values as shown in this last column, really the cutoff is right here. And let's recall that the lower, more negative that pKa value, the stronger the acid. So for really strong acids, that means the conjugate base is weaker. So that's the inverse relationship. So if that's weak, it means that it's stable, it's happy, and it's a good leaving group. So this line right here is basically from positive to negative, or in general at zero. So if you look at the leaving group, its conjugate acid, you really want the pKa value of the conjugate acid 0 or negative. If something leaves, you look at the conjugate acid and the pK is above 0, that is not a good leaving group. So that ties in structurally of what you can use to make this reaction happen. So for the most part, SN2 reactions are run with chlorine, bromine, or iodine. We'll see an example with oxygen in a little bit here, but we want to use one of those halides, and the rate is iodine is better than bromine, it's better than chlorine, and then fluorine is not a good leaving group. So I want to say one more thing about that, but I'm drawing a blank at the moment. So yeah, I guess the connection with these, remember how we install those using the radical CH substitution. So with the table here, it's pretty specific to methyl. But when you're looking at a carbon backbone and you want to install a halogen, you have to think about chlorine versus bromine as the two main reagents we used, and what are the pros and cons of each. One thing about SN2, say that you made a chlorine leaving group, you can actually do a halogen substitution of chlorine for iodine using SN2. So what I mean by that, say for example, we started with propane, and we know that it can form those two possible chlorinated products. Say somehow we were able to separate those, but then we didn't want to use chlorine in a subsequent SN2. We could take, say we were able to isolate the chloropropane. You can treat that with sodium iodide in a solvent to make the iodo-propane. And so of these two, this is the one with the better leaving group. And practically speaking in the lab, sometimes that matters. So that's just a halide exchange, and it occurs through SN2. So fluorine is not really a halogen we want to use. OH minus as a leaving group is not good either, because the conjugate acid, which is water, has a pK of 14. And so we want the pK of the conjugate acid of the leaving group to be 0 or below. But alcohols as a functional group are very common in organic chemistry, and we want to do things with them. So what we can do is activate it. And if you look at that hydrogen, essentially what we're doing is substituting that hydrogen for this other thing here, and overall it makes that a good leaving group. So maybe what I'll say is we're don't want to do that. This H is going to be substituted for that thing in blue there. And then overall, that is a good leaving group. And that's called a sulfonate ester. So we can't just treat this with a nucleophile and expect OH minus to leave because hydroxide is not really stabilized according to the pKa argument. But we can take the H, transform it from an alcohol into a sulfonate ester. And on the next slide, I'll show the mechanism by which this happens with this reagents, but this thing sort of resembles sulfuric acid with some modifications, but sulfuric acid is a strong acid, and then its conjugate base is stabilized. So the same principle operates when we do this transformation. So before I show you the arrow pushing of this, let me just point out, notice we have an H and a Cl. And so that forms HCl, which is an acid. And then in the reaction, we have a base that will neutralize it. So one way of talking about this is it's a functional group transformation, but it's also a condensation. We produce what we want, and then this small molecule HCl, and we neutralize it with the base. So this oxygen gets bonded to that sulfur, and then HCl is a byproduct. So mechanistically, let me show you how that happens. So we know oxygen and sulfur are both heteroatoms. And so they're in the same group. Sulfur is below oxygen. In terms of electronegativity, they're kind of similar. So we could ask, why would oxygen attack something that's also electronegative? But it has these other heteroatoms bonded to it. So we can think of the sulfur as being electron deficient. So when two electrons move, it can attack sulfur. And so now we have to break a bond. In the choice of doing that, we ultimately need the chlorine to go away, but not quite yet. The weaker bond is one of these pi bonds. So we'll push the pi electrons up to the oxygen.
Can you say again why the sulfur is electron deficient?
So in this little periodic table here, oxygen and sulfur are in the same group. So their electronegativities are going to be kind of the same. So in theory, you wouldn't want something of similar electronegativities like attacking one another. But the fact that the sulfur has 1, 2, 3 heteroatoms bonded to it, those are kind of pulling electron density away from sulfur, and then that makes that kind of delta positive. So another reason why this works is sulfur is in the period below oxygen, so it can have more than an octet and have these different molecular geometries. So if you look, this has kind of more than 4 bonds, more than 8 electrons. So at this point, what will happen is this lone pair will collapse back down to form an oxygen-sulfur double bond. And since we're making a bond, we have to break a bond, and then chlorine is the best leaving group to leave. At this point, we have the conjugate base of HCl here, and then we have this amine base. Due to a pKa argument, the amine base is what is going to abstract this H from the alcohol. And then that will form the ammonium or nitrogen positive species, and it's balanced off by the Cl minus. So that's one way of writing this, where I use that little dot. Another way that you might see is where the hydrogen is actually bonded to the nitrogen has a plus charge, and then the chloride has the minus charge. But these are communicating the same thing as that byproduct, which soaks up the HCl that's generated. And so now, as I said, this whole thing in green is the leaving group. So a nucleophile can attack the carbon. We then break that carbon-oxygen bond. The negative charge that ends up on the oxygen is resonance stabilized across these other two oxygens. So that mimics the acidity of sulfuric acid. On the next slide, we'll show you what is meant by this R group. What that can be and what factors influence its leaving groupability. So just like with chlorine to bromine to iodine, they have different rates. Depending on what this R group is, those will have different rates as well. So for now, let's just consider the general thing where R can be these things we'll talk about. And so we're going to use sodium bromide as our nucleophile. So the bromine has now a negative charge, and one of these lone pairs is going to attack the carbon. And then we break the carbon-oxygen bond. So that whole group has now been substituted for bromine. And so we balance the spectator cation with the leaving group, and that's the byproduct.
What's the byproduct?
So the sodium sulfonate. So to just show you one of the resonance hybrids, that negative charge can migrate So this leaving group is happy because the negative charge is kind of dispersed over all three of those oxygens. So if we were trying to displace OH, that's a bad leaving group based on the pKa. But what is the R group? So this whole kind of thing stays the same, but we can change R to these different things. This first one has the form That's what this p-tol means. That means para-toluene. So R is this benzene ring with a methyl group. And the leaving group is this thing. The conjugate acid is just where you're protonating that. And then there's the pKa values. The next one, the R group, is just methyl, CH3. And then the best leaving group is where the R is CF3. So the conjugate acid of that is called triflic acid, and it has a pK of negative 14. So that's kind of the hottest leaving group you can use in terms of its reactivity. This first one that I drew out is nice for a concept that will cover more in organic too. You've kind of been exposed to it already in lab with thin layer chromatography. You spot something on a plate and then you use UV light over that plate. Did you do that? So you shine the UV light on it and then it should hopefully, show like a purple bluish color. So that benzene ring is what is responsible for that. It's called a chromophore. When R is methyl or CF3, those don't have chromophores, so you can't visualize them with UV light. So there's pluses and minuses to all of these choices. This one you can track. These, it's a little bit harder to see the progress of taking the alcohol to the sulfonate ester. But again, what you'll notice is that pK values are all below 0. And so now we have these two classes of leaving groups, either the halogens or these sulfonate esters that we can work with. So that's the leaving group electrophile part. The next thing is the solvent. We want to be aware of the factors or influences that are important for the solvent, which is an organic molecule in and of itself. How does that influence, the conversion of the reaction and the rate? So solvents really have many purposes. The primary one is to get materials into solution. So if you have two solid things and you mix them, from now until the heat death of the universe, they probably will not react unless you apply some other special technique to them. So you need to get those solids into solution so they dissolve things. Another one is they act as a heat sink or a heat source. So if the reaction itself is exothermic, the solvent can absorb some of that heat and control it to a certain extent. But if we think about the reaction coordinate and there's a really high energy of activation, like ambient temperature, what we're sitting at now is typically about 25 degrees Celsius. if that heat is not enough to drive it over that rate limiting step, we have to apply external heat, and the solvent helps take that heat and increase the number of productive collisions for the reaction to occur. So that's a variable that helps manage the sort of chemical engineering aspects of these reactions. The specific class of solvent for SN2 is polar. So there has to be some polar covalent bond in there, and then aprotic. And that really means no functional groups with alcohols or amines. So no acidic hydrogens. And I'll show you a little picture of why that is on the slides coming up. These are the most common solvents used for SN2 reactions. So here's the name, and then they're shown structurally on the bottom of the slide. They're given these abbreviations, and as we learn more reactions, a lot of organic chemistry is kind of knowing the nomenclature and the abbreviations for things. So acetone, the IUPAC name is propanone, that's a ketone. HMPT, the functional group class is something we haven't really seen before. It's kind of like an amide, but there's a phosphorus, so that's called a phosphoramide. We've seen nitriles, so this is acetonitrile. DMF is an amide, so dimethylformamide. And DMSO is dimethyl, and then this group is called a sulfoxide, so DMSO. The two key things about this, number one, they're all polar, so we have a carbonyl group that's polar. Here we have a phosphorus-oxygen double bond, that's polar. Nitrogen-phosphorus sigma bonds, those are polar. Nitrile, the triple bond's polar, so that's the polar part. And then you'll notice none of these have OH or NH functional groups, so they're aprotic. The boiling points are important because if we do have to apply heat, DMF and DMSO are usually the ones that are employed most often because then you can really crank it up. And again, if you're thinking about water at 100 degrees, DMSO, you can go to about twice that. And cold glass looks like hot glass in the lab, so if you're not careful and you don't know the temperature, if something's 189 degrees, it'll burn you pretty quick. But, you know, according to the Arrhenius law from Gen Chem, for every like 10 degrees you put in, you're changing the rate. So you can get a lot of rate changes with this solvent. Practically speaking, the absolute pain in the butt thing about working with high boiling solvents is eventually you have to get rid of it. And you know, if you're producing a product and then you have a lot of this high boiling solvent around, it's really hard to distill it out without decomposing your product. But fortunately, due to these characteristics, when you do an aqueous workup with water, they're usually miscible, and that strips a lot of that solvent out. This other thing which may be new is called dielectric constant. And the way that I like to think about this is just the permanent dipole moment of the molecule. And because we're talking about ionic reactions and the mechanism is polar, so you're forming these, or you have these anions and stuff present, you want a solvent that's going to help facilitate the mechanistic intermediates along the reaction coordinate. So the larger this is, the more it increases the efficiency of the reaction. So DMF and DMSO are commonly used, but acetone and acetonitrile are kind of the first choice because the boiling point is lower and they're easier to get rid of. So why are these polar and aprotic, specifically the aprotic part? So the stronger nucleophiles will typically be of this form where you have some metal cation and then an anion that's negatively charged. So that's ionic. And for the SN2 mechanism to happen, the nucleophile has to supply those electrons. You know, if you think of the metal and the anion in a relationship, if that relationship is strong, the reaction is going to proceed slow because the electrons are not available to bond. The solvent helps break that up by coordinating with the metal. And here's a crappy little depiction of that. The metals plus, you have this polar functional group that will coordinate around it. And, you know, this is flat. But if you think of the metal as like, you know, some sort of ball, and then the solvent is surrounding that in 3D. So, I mean, there's going to be a lot of solvent around that. And so it's moving the metal away from the nucleophile, and so we use this word exposed or naked. Now the nucleophile is out there, it has to react. Its partner is being shielded by the solvent. So that's another reason we want this class of solvent or organic molecules. So I kind of just verbally went through that, but again, the reason I'm sort of belaboring this point, so right now we're learning SN2, so substitution, nucleophilic, bimolecular. And we said in the trend of leaving groups, if something's tertiary, you can't substitute it. But there's more than one way to skin a cat. Apologies if that offends you, but if you do have a tertiary substrate, how do you substitute it? Well, it happens through a different mechanism called SN1. And that uses a different class of solvent. So as we learn more of these reactions and you see stuff, you know, starting materials with functional groups, reagents and solvents above the arrow, you have to like start putting all these pieces together to know what mechanism is occurring. So the next factor is the strength of the nucleophile. So any element can typically be a nucleophile as long as it's able to supply the electrons as the Lewis base. So here's a periodic table, and the blue arrow shows you the electronegativity trend. So fluorine's the most electronegative, and then the elements increase going left to right across the period, and then up towards fluorine in the group. So that's electronegativity. Nucleophilicity So the ability to supply those electrons is the opposite trend. So moving away from fluorine, the ability to act as a nucleophile increases. So right to left, and then down the group. So that's the periodic or elemental part of that. When you're comparing sort of the same thing in terms of like an acid, water, or its conjugate base, hydroxide, the thing that's negatively charged is always the better nucleophile. Again, because that is supplying those electrons. They're primed and ready to go. If water were used as a nucleophile, it has these lone pairs, but in the SN2 mechanism, you're eventually going to have to get rid of one of these OH bonds. And that's going to affect the transition state, that trajectory of attack, and then ultimately lead to sort of another ravine in transition state or intermediate. So when you're comparing, kind of like species, the negative charge, the anion is almost always better than the neutral. If we have different nucleophiles, again, moving from right to left, the nucleophilicity increases. So of these negatively charged ones, the heteroatom bearing the negative charge, nitrogen's better than oxygen, is better than fluorine. And then if carbon were on here, if I made it that way, carbon would be the best one. So there's a lot of things you have to diagnose when looking at reactions. So for this module exam, really what we're looking at is the radical CH substitution and then just these substitution mechanisms. Your last module is on a different mechanism called elimination. And so all of this complicates things because you really have to know the reactivity of the reagents you're dealing with and how they apply to the functional groups in the starting material. So here's the fun organic chemistry version of Mad Libs. As we fill in the blanks, what gives the best possible true statement? I think I heard C. So the nucleophile supplies a lone pair of electrons to attack the electrophile at a trajectory of 180 degrees relative to the leaving group. So that really is just verbalizing how you draw the arrows in the ionic mechanism. So now that we're familiar with the general aspects of that mechanism, what are the different nucleophiles according to the elements? and then what are the products of these substitution reactions? How is this useful? So for the first couple slides here before we get into the stereochemistry part, the electrophile is just going to be methyl bromide. So that's the constant thing, and then we're just substituting the bromine. In the first reaction on this slide, which is showing 2 carbon nucleophiles, so that's a negatively charged carbon atom. So potassium cyanide is a good nucleophile because it has the metal in the anion ionic form. That carbon will attack the electrophile, displacing the leaving group. And then you'll notice we've done the substitution, and we end up with a nitrile. The potassium bromide is, again, the byproduct with the spectator potassium and then the Br- leaving group. So we learned about nitriles. So because they have the triple bond, we can see that in the IR in this 24 to 2200 region. The other thing we can note about the cyanide reagent is we have 1 nitrogen, so the parent mass should be an odd number. So we can relate that back to the mass spec. So as we move forward through all these different nucleophiles, the thing you want to keep in mind is how are you going to identify them with IR, mass spec, and NMR. So from cyanide, the next nucleophile we're going to look at is synthesized from a terminal alkyne. So when we were learning about pKa and the hybridization effect on carbon-hydrogen bonds, we saw that sp hybridized carbon H bonds were the most acidic of that trend. So that's found in a terminal alkyne. We can deprotonate this H with sodium hydride, so that's an acid-base reaction. And this generates this thing called an alkynolide, where now the carbon is negatively charged, the sodium's positively charged. And mechanistically with the arrow pushing, it's the same. The lone pair attacks the carbon bearing the leaving group. And so the bromine has been substituted for all of that stuff. When you're taking notes and doing problems, of this nucleophile, that carbon is doing the action, but all this other stuff still has to come along. Nothing's changing in it, so don't forget to draw it in your products. And overall, what we've done from our starting alkyne, which was terminal, we've now made an internal alkyne. So those are just two. That's the appetizer of carbon nucleophiles. There's many more, but those are, the introductory ones. Any questions? So we're just going to move across the periodic table here from C to N now.
So would you be asking us to identify the products and given some reactants, or both that way and the other way around?
Probably both ways, yeah. So nitrogen nucleophiles. We started off this semester when we were learning about bonding and the different elemental patterns of bonding, how many sort of bonds, lone pairs that make up an octet. And so ammonia was one of the first things we learned about. Ammonia has a lone pair of electrons that can attack the carbon bearing the leaving group. And so we've substituted the bromine now for an amine group. Ammonia itself at room temperature is a gas. It liquefies at -33. So there's kind of practical issues. If you've ever smelt ammonia, it is very stringent and potent. But there's a reactivity issue of why, on paper we can draw that, but practically this is not useful to use just ammonia as a way to introduce nitrogen into a molecule. And the reason deals with this product that we form is a primary amine. That nitrogen also has a lone pair. So what ends up happening is it can also act as a good nucleophile. So you're forming it in the reaction while you still have ammonia present. And you're like, well, yeah, I just want to use a one-to-one mixture of this to isolate that. But these coupling partners of nucleophile, electrophile don't just get together at all the same time to convert. So if you have some of this in there, it can react with that. And so it'll do its own SN2 reaction to give you a secondary amine that has a lone pair. That's a good nucleophile. So it can get alkylated. It can form the tertiary one. And ultimately, it'll stop when the nitrogen no longer has any hydrogens or lone pairs remaining. So synthetically, ammonia is not good because you'll probably end up with a distribution of these things. So we're not quitters, so we're not going to throw our hands up and give up on nitrogen. Fortunately for all of us, people have developed alternative reagents to get nitrogen into molecules. And really what you'll see in these, the nitrogen's not bonded to any hydrogens. And so that's part of why this is an issue. And then also, as soon as that lone pair is consumed in the SN2, it can't regenerate another one through losing a hydrogen. So the two main reagents are called sodium azide and potassium thalamide. These are both ionic compounds. we have a group 1 cation, sodium or potassium. Since those are +1, the nitrogen is balanced off by a -1. Am I doing that right? I hope so. Having a pre-elderly moment here. Pardon me. So you have this plus minus. For some reason that doesn't look right to me, but I can't explain why. So again, the arrow pushing is the same from the nucleophile to the electrophile. And what that is doing is installing this azide, which is N3. And we can take that, do some more stuff on it to get an amine. But really, that's kind of more organic 2 stuff. We're just concerned about how do we get nitrogen into the molecule. Sodium azide's nice. It kind of looks like table salt. It's a white solid. It's easy to handle and weigh out and all that stuff. The other reagent, potassium thialimide. You have K plus. The nitrogen's minus because now it has those 2 lone pairs, its original one plus the extra one to give it the negative charge. It will do the SN2. Now you have the nitrogen in there. This sort of one part of that should look like an amide to you, but the fact that there's 2 of them, you'll notice the vowel change from A to I. This is called an imide. The atom economy issue of sort of azide versus thialimide, really all this extra stuff is there to just bring the nitrogen into the molecule, and then this is eventually removed. So people that scale up chemical reactions, process chemists that make like metric ton quantities of things, when you do a reaction, you really want everything to be included in the final product, and you don't really want to be dragging along a lot of extra mass that isn't ending up in the thing that's being sold. So conceptually, these work fine for SN2. I can attest to the fact that they work because I've done it in lab, and if it works for me, it'll work, basically. But getting rid of that can be kind of a pain in the butt because it produces a byproduct that you have to eventually separate. So azidation, and then this one's called the Gabriel amine synthesis. That's the person that invented it. So with the nitrogen-nitrogen triple bond, you can see that in IR, the same sort of region from 24 to 2200. And because we have 3 nitrogens, the parent mass will be odd as well. And so those are ways of validating that it's in the molecule. For the thialimide, This carbonyl type stretch will again be below 1700, similar to amides. And we have one nitrogen, so the parent mass is again going to be odd. Any questions on nitrogen? So we're moving along our journey here. C to N, now we're at oxygen. Probably the most famous name reaction for Organic Chemistry 1 students everywhere is the Williamson ether synthesis. And this is where things can get tricky and why I've designed the class in the manner which I have. This reagent is called sodium methoxide. For SN2, this is acting as a nucleophile. So it's going to displace with the normal arrow pushing, and what you end up with is carbon, oxygen, carbon. So that's an ether. Where things get tricky, specifically related to the final exam, when you're looking at a reaction, these negatively charged oxygen species can really act as either nucleophiles or bases. So remember the difference in what that means. A nucleophile is typically forming a bond to carbon. An acid base is the deprotonation of a hydrogen. So in this example, you can't really do an acid base because there's not more carbons to deprotonate from. But in more complex electrophiles, there's this competition between nucleophilic substitution and then acid-base chemistry, which is a different mechanism. The way you distinguish between those mechanisms is identifying the class of electrophile, the solvent that's used, and then the temperature. So for this specific module, we're only really dealing with substitution. Module 5 is elimination, and that gets back to the acid-base stuff. But the final exam is the Wild West, and you're kind of on your own to figure out what these reagents are doing. So with the spectroscopy of ethers, there's nothing distinguishing about them, so they're really hard to figure out with IR, NMR, or that sort of thing. I can't really say, look for this, that, or the other, and it's an ether, because it's not really that way. There's no unique mass signature. The IR signatures are in the fingerprint region, which we're not really analyzing. So for these, you just have to diagnose what you're starting with and then what sort of answer responses are. The next oxygen nucleophile is starting with the conjugate base of a carboxylic acid. So if we started with ethanoic acid and we treated that with potassium hydroxide in water, that would do an acid-base reaction to generate this species with K plus O minus. And then that can attack the electrophilic carbon. The leaving group leaves, and now we've made an ester. So in terms of the spectroscopy, again, the molecular formula must have at least 2 oxygens. There's a degree of unsaturation for the carbonyl group. That carbonyl stretch will be between 18 and 1700. You also have an sp2 hybridized carbon that you can look for in the carbon NMR. So there's more features that you can put together in terms of like fragments and data to arrive at the claim of an ester. So we went from C to N to O. The halogens, as I said, we get them into the molecule using the radical CH substitution. Once they're in there, you can displace them with another halogen. So we don't really need to go over that SN2 process. You would use like sodium iodide or potassium iodide if you wanted to use a halogen as a nucleophile. So we'll do some questions to see if this is clear or not. So we have 4 electrophiles where the leaving group is constant. It's bromine. And the question is, if you imagine you had all of these in a flask, the solvent is acetone and you added potassium cyanide, which one would react first? So let's do the Monty Hall problem here. Not sure I understand that problem completely, but which one can we totally eliminate from contention? So C is out. That's an sp2 hybridized carbon, and we cannot do SN2 on that. So we have A, B, and D. So of those, which one's going to be the winner? Thought I saw a B as in boy. It's close, but not quite. D? So D is the correct answer. So how do we arrive at that? The first thing you always want to do, look at the carbon bearing the leaving group and then classify it. So we have secondary, we have primary, we have primary. The rate trend is methyl is greater than primary is greater than secondary. So that eliminates that because we have 2 primaries. The difference between them, that one is allylic due to this double bond. So it's primary and allylic, so its rate will be faster than this primary. So, as you do problems and you're reading and things, there's really just an algorithm that you're following for, classifying or diagnosing things that will lead you to different decision points and then ultimately should funnel you into the correct answer. So the ACS standard exams are fond of these sort of responses for things. So we have 3 substrates. They all have bromine as the leaving group, so that's constant. And we're doing an SN2 with sodium methoxide and DMSO. So the trend is which one reacts the fastest to the slowest. So when you see this on your final, make sure you understand what these greater than or less than things are in relation to the intent of the question. So for this, which one reacts first? So I think I heard someone say second. So this reacts first. Then what reacts second? So it will be that order, which just so happens with the canned responses here is B. And we're doing the same thing. So primary, secondary, tertiary. So we're able to solve the intent of that question by classifying the leaving group. So what's nice about this one, like why it doesn't react, this is a bicyclic compound, so there's a ring that's bridged. The bromine is tertiary. Based on the SN2 mechanism of how the nucleophile has to approach that leaving group, you can see that this carbon sits directly behind that one. So in nucleophile, unless there's some weird quantum flux, it cannot exist at the same time and space as that carbon. So it's completely blocked from getting to that antibonding orbital. So substrate 1 is out for SN2, but as I said, we can't just rest on our momentum. When you do have tertiary substrates, you can substitute them. It's just the mechanism is different, which means all the other conditions are different. So here we have a secondary iodide that has been substituted for an azide. So we know that iodine is a good leaving group. And so which reagent would be best to do this type of substitution? So sodium azide. So A and C are out, obviously, because there's no N3 at all. This reagent B, which is probably new to you and looks weird. The reason that's not used is because that is a polar covalent bond. With sodium azide, it's ionic. And remember when we talked about something being an anion versus being neutral? The anionic one is almost always the better nucleophile. So yeah, these things, if they look weird, they do exist. People have some specific organic chemistry kinks where they try to make very weird things to look at their properties. When you get into a lot of heteroatoms like this, typically those are like high energy materials. You can think of what those are used for. So just pay attention to what's kind of going on and what makes the most sense when you diagnose these things. So let's see where we're, just do this one and call it a day. So when you look at any alkyne, conceptually they can be made two different ways. So our target molecule is 2-hexyne. And so we want to look at what pair of these reagents and the answer choices would be best to make 2-hexyne. So the first thing to consider is how many carbon atoms are in the chain, and then where is the location of the triple bond. So what do we think would be the best answer? So A is the best answer here. We have this sodium alkynolide. This would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So the nucleophilic carbon attacks the electrophilic carbon. That makes the alkyne with the double bond at the correct position starting at 2. Choice B is not correct because if we count the carbons, we have 1, 2, 3, 4, and 5. So we need 6. C, that would make the 7 one. Then here, this could become a nucleophile, but the issue here is this has no good leaving group. You can't have H- as a leaving group due to the pKa argument. But let me just draw that real quick. So there's 1, 2, 3, 4, 5, 6. I said we could do this two ways. And really what that's relating to is how you break down where you're putting that negative charge and then what ends up being the electrophile. So choice A broke that bond. Another way you could do it is break that bond where the negative charge is there, and then you have a 1-carbon electrophile. So as we move forward through these reactions, we'll talk about that sort of thing, what is feasible in terms of accessing those functional groups, and then how do we identify them with spectroscopy. I think, yeah, we'll probably